So hello everyone, my name is Kalinani. I'm a postdoc here at RIT, and today I'll be giving you a very brief introduction to GRMHD. And to give you just a quick overview of my talk, starting with this basic formulation of this GRMHD equations, and then I'll cover some high resolution shock capturing methods and this primitive to conservative inversion routines. And then just quickly describe the code workflow that are typically adopted in GRMHD codes. And the second part of my talk, I will be focusing mainly on *X, which is a new GRMHD code coming up. And it's been spearheaded by many of us at RIT as well. So here I list a couple of resources. In terms of books, you have, these are some of the favorite ones that I go look onto. If I, for example, you have the Numerical Methods by Levesque, it's my favorite, and then you also have like numerical derivative book from Baumgart and Shapiro, as well as the relativistic hydrodynamics from Rezzola and Zanotti. And here below, I also share some articles. One of main interest could be this this article from Anton et al., which basically describes these GRMHD equations. So needless to say, to understand the various different astrophysical processes involved in different events such as binary neutron star mergers, core collapse supernovae, jet physics, accretion disks, you need GRMHD simulations, as magnetic fields in these situations can be fundamentally important. And for instance, one example would be this Luciano Combi's talk on Tuesday, who would be talking about jets coming out of the, for instance, from binary neutron star mergers. So stay tuned for that. So Alexandru today earlier gave an excellent talk on the background of numerical relativity, so it did most of the work. My job became easier, but we now understand the motivation behind numerical relativity, and not only evolving space-time, but also for, if you want to evolve matter equations, MHD, you need numerical relativity, and the typical standard approach is a 3+1 foliation. So the technique, and for instance, now for evolving space-time, you have the BSSN or the CCZ4 formulations. That you can typically evolve using Einstein Toolkit. For example, the McLaughlin was mentioned earlier. For GRMHD evolutions instead, which are typically based on the Valencia formulation, can be evolved using different GRMHD codes that exist in the community. Some of them are listed here. Now, the Valencia formulations considers the set of GRMHD equations as a first-order flux conservative hyperbolic form, a generic form, which I show here, where U is essentially the state vector. F stands for the different fluxes for these state vectors, and S stands for the sources. And here you can see that here you have also the expression for T mu nu, which was generally adopted. And non-zero source stance means that fluid can actually interchange energy and momentum with the space-time as well. So this is, so here you have different primitives, is what we call the fundamental variables, which are the rest mass density, fluid free velocity, specific internal energy, and you might also want to evolve electron fraction, YE, and you have other terms that could be computed from these primitives, for example. And then based on these primitives, you have certain analytical expressions that will allow us to compute these conserved quantities. So here is what the different state vectors that I mentioned earlier. This is basically dense, conserved density D, capital V is usually used, or conserved momentum. And then you have conserved internal energy, tau, and then you might also have, if you want to compute conserved magnetic field as well as electron fraction. Typically, most GRMHD codes work under the assumption of idle MHD. That means that you consider a perfect fluid which has infinite conductivity, and also this means that the co-moving observer measures no electric field. And based on this assumption, you can rewrite your Maxwell equations solely in terms of B. which I show here, and which these equations can then further be separated out to the divergence precondition and your induction equations in B. And here I also show some of the co-moving magnetic field components that can be computed in terms of the Eulerian big B. So what is written here? Now, instead of evolving the magnetic field directly, one can also choose to evolve the vector potential. And so here you have your curly A as the 4-vector potential, which is written in terms of the scalar potential plus the 3-vector potential. And here in this case, you have these induction equations written in terms of A. And then once you have your A, you can compute B from the curl of A. And the big advantage of this is it automatically, evolving the vector potential is that it automatically satisfies the divergence precondition. That can be problematic in cases when you're directly evolving B, and it can lead to spurious effects, and unless you make sure that your divergence of B is always remain to 0. Now, to evolve this induction equations for A, you also need to choose a gauge. So the simplest option is to use this algebraic gauge, where you set your scalar potential phi as minus nj ha, or in this case, this is how it's written. And then in that, it's what you'll essentially get is you're evolving the induction equations by computing this, in layman's terms, V cross B, by basically just the electric field. This term goes to 0. A more commonly used gauge is the generalized Lorentz gauge, which is shown here. And this involves also evolving an extra equation for the scalar potential, which I mentioned here. Now, apart from that, to close the system of equations, you need an equation of state, which is basically what pressure you have in your system. So depending on the astrophysical problem you have in hand, there are different kinds of equations of state that exist in market. And the simplest forms are the analytical one, where you describe the behavior of an ideal gas or the polytropic gas. And then you can also have the more complex ones, which are tabulated, which could be a one parameter, or even the complex one, including 3 parameter, where pressure is a function of density, temperature, and the electron fraction. These are more typically used, for example, in neutron star merger simulations. And you can also have a hybrid equation of state, where you have a cold polytropic pod and a thermal pod as well. And on below here, I show, for instance, there are different piecewise polytropic approximations used for instance, the cold equation of state, where P is a function of density. Now, once you have all of that, you want to evolve your equations on a numerical grid. So here, for instance, I show you a simple numerical grid on top left, where you have the spatial variation on the x-axis and the time variation on the y-axis. And since you have initially your conservation equations in integral form, you want to discretize them. So the first step is you compute the cell averages for your state vector or your solution, and as well as you compute your numerical fluxes like this. And then you can write your conservation equations in a discretized way, in like I stated here and below. And typically for numerical cell in a GRMHD simulation, you have different places where you store your variables. For instance, your primitive variables would likely live in the cell centers, and you have your magnetic field components living on the faces of the grid cell. And you have your vector potential, in case you choose to evolve vector potential, typically live on the edges. And so does the electric field. And you might also choose to have your metric components either the cell center, which is typically the case for when you're using performing simulations with carpet, or these might be located at vertices in case of carpet X. Now, when you want to start your simulation, you need some initial data, as we had a great talk earlier, just before mine. So even if you have a smooth initial data, once you evolve that, you could develop some kind of discontinuities. And to capture such discontinuities and shocks, we need very high resolution shock capturing techniques. And these techniques are basically should also obey the correct Rankine-Hugin conditions. And they're basically a two-step process. The first step is to reconstruct your primitive variables, for instance, to the left and right faces of the grid cell. And there are typical schemes that are used for this is second order accurate min-mod or third order accurate piecewise polymorphic methods. And then once you have your once you reconstruct your fluxes, and then you can compute solve them using applying approximate Riemann solvers. And this is typically used in literature or Lax-Fredericks or the HLLE solvers. So as I mentioned earlier, for any numerical scheme to converge, they should be able to satisfy these Rankine-Hugin equations. I don't know much into detail for that, and just wanted to mention that once you discretize your solution, you automatically create these local Riemann problems, and these can probably evolve later into either shocks or refractions and produce these contact discontinuities. So to solve that, the first step is, like I said, reconstruction. So this is typically the standard, the most simplest one is this min-mod reconstruction. So for that, you need to make sure that you have the total variation diminishing property that is obeyed by such a reconstruction scheme. So for instance, for the given solution UN, you have the total variation given in this form. And you want to make sure, and this essentially measures how much oscillation that you have in your solution. And then you want to make sure that as you evolve your solution in time, there should not be any spurious oscillation, so you can have a robust evolution. So these total variations should not increase in time. So we have these slope limiter methods, which typically obey such properties, and you use a simple linear reconstruction on the cell faces. So for instance, you have your solution UNJ, which can be rewritten as in this way, where you have sigma, where is the slope, and you employ this min-mod scheme, which is mentioned here, and then using that, you can basically get two extremes of each cell. So for instance, you have your cell at J, and you have the two extremes on the left and right of the extreme faces. You do the same game for J+1, and at the common interface of these, you have created a Riemann problem. And now you want to solve this Riemann problem, right? So that's the next. So before I jump into that, again, I wanted to show you the piecewise polymorphic approximation method. Piecewise parabolic method. Here, you instead of a simple linear reconstruction, you use a parabola, more or less, a parabolic function, and then you try to reconstruct a bit more accurately in a similar way that I mentioned earlier. And then the next step is to employ Riemann solvers to compute the fluxes at that interface too. And as you probably know, that hyperbolic PDEs have this finite propagation speed, and then that you can have only there is a limit to the characteristic speed of the system. And the structure is essentially given by these eigenvalues of the Jacobian matrices of the system. So you need to know, you have to compute these eigenvalues, and the simplest approaches you have from HLLE, you have these two-way approximation, where you have this initial discontinuity and decays over time. You have what you call, you want to compute what is the state in between them. And here you have the characteristic velocities, lambda r and lambda L, where we have the discontinuity move this space propagating in two opposite directions. And from Anton et al., you might find that this prescription for these characteristic speeds. And then using that, you can compute your state vector for UHLLE, as well as your fluxes FHLLE at this discontinuity. And a simplified version is when you assume that your the speed of your right-going wave is negative times the speed minus the left-going wave, and you get a simpler solver, which is called the Lax-Friedrichs one. Now, the last important core element of a GRMHD scheme code is a contour prim, which essentially stands for conservative to primitive. And currently, there exists no analytical solution to compute your conserved variables, primitive variables from the evolved ones that are the conserved variable. So you need to employ some root finding techniques in order to retrieve these primitive fundamental variables. And these are essentially called contour prim C2P schemes. And currently there are different C2P schemes existing in GRMHD, which are Noble et al., Duran et al., Nielsen et al., there are many. And Siegel et al. 2018 gives a really good review of these different contour prim schemes that exist. And these schemes could all certainly fail in certain regions, for example, in very high Lorentz factors or very high magnetizations. So, and typically the types of method used in these schemes are either Newton-Raphson, based on Newton-Raphson techniques, which are when you start with an unbounded region of where your root lies, and usually you need to provide an initial guess. And then this also depends on US derivatives. While there are also root bracketing techniques, where the root is already, you have to provide bounds, but they might not depend on the initial guess and on the US derivatives. They are more robust, but usually slower. So here, for example, I talk about quickly about the Noble contour prim. So you have this recovery problem, which is essentially 5-dimensional. You don't know the density, you don't know the three velocities, and you don't know the specific internal energy. So you want to know these primitive variables. And Noble et al. Essentially reduces this dimensionality problem to 2D, and introducing these two scalar quantities, z and v squared. And then you try to solve for the roots for these two equations, for z and v squared essentially. And once you have found the roots using applying some kind of Newton-Raphson method, you can then eventually compute your density from the v square, as well as your three velocities, and then also compute your specific internal energy using the equation of state. So to summarize and quickly describe.
There is a question about this in the chat.
Yes. What is the example of root bracketing that not depending on the, isn't that problematic? So I think if I remember correctly, there is, for example, the Reprimand scheme does not depend on the US derivatives. And US derivatives can be problematic. For example, if you have really sharp germs, or if you have jumps, or if you have, in some US tables, you might have maybe even negative specific internal energy, and you can get spurious values or negative values, or so root bracketing schemes are generally more robust. And yeah, so that's one example I could think of. I think even one D Palenzuela scheme also does not depend on US derivatives, but I'm not 100% sure. I have to double check.
So I think the question was not, I think maybe the confusion was not depending on EOS versus not depending on EOS derivatives.
Oh,
because if we look at,
oh, sorry, maybe I missed it. Example of root bracketing not depending on the EOS.
Is it the question time now, or have we just finished the talk, right?
No, it's not. The talk is not finished, right?
No.
Well, let's go on with the talk and then address the questions.
Yeah, I think they meant EOS derivative. So yeah, I think I pressed that. That's okay. Yeah, so just to summarize and understand in a very rough schematic way, what is a typical workflow of such GRMHD codes? So again, to recap, you want to solve such kind of an generic equation of this form. So the first step is essentially to initialization. And you define your primitive variables, you provide some initial conditions. And then the next step would be to do a primitive con. So you want at your time, once you have your primitives, you want to compute the conservatives. The conservatives are the ones that actually evolve in time. So you want to do the primitive con step. And then after that, once you have your, you can do your compute your source terms using finite difference schemes. And next would be computing the flux terms. And this is essentially employing these high resolution shock capturing techniques. And finally, once you have source minus flux can give you an ODE in which you can then solve using time integrators like Runge-Kutta form. And finally, for the next time step, you have to do a con to prim. So you compute your primitives for the next time step. And then you can, this can go on in a loop where you evolve your core, your system in hand until you reach your results or failure. So I just wanted to ask if you have any other questions or comments. Yeah.
On the previous slide, so your source terms can contain derivatives of the primitives of consecutive variables?
I think they have derivatives of the space-time for sure.
Mm-hmm.
So that's what you compute using finite differences. Yeah.
But you can't have primitive or conservative variable.
So you for source times you use primitive. You have primitive variables because you're essentially computing T mu nu.
But not derivative,
Not the derivatives as far as I recall. Yeah.
And if you do have one, is that like completely ruin your Riemann solver and everything, or is it just like a degradation?
Oh, that I'm not completely sure of. Yeah.
I've seen one code that does it with one variable, but that's a magnetic field variable on one of the codes. You do have shocks in there, so that would be good.
What?
Yeah, I was hoping to pull up the chat question, but I couldn't find it. Oh, you have to hold a button.
I think I already probably addressed it. What is the example of?
Yeah, just want to make sure we saw. Questions, more questions? No questions? Okay, let's thank our speaker.
Oh, no, it's not on.
I thought you were done. I thought this.
No,
Oh, I'm sorry.
the second part.
I'm sorry.
My apologies.
I thought
Not
you were done.
finished yet. So now I would try to introduce our new GRMHD code called Astrex, which is based on the CarpetX infrastructure. This is basically spearheaded by some of us at RIT and includes also Eric Schnetter, Roland Haas, Federico, our Italian collaborators, as well as students of Eric. So you already heard from Eric about Amarex. So I would not go much into detail. And then on Amarex, we have this new CarpetX infrastructure. And you already heard from Eric about that. And again, not going into all the important features, but just wanted to mention that Alan Wen here at RIT is also working on some binary black hole simulations using CarpetX, and he's also working on some interesting moving box mesh refinement, implementing porting over to CarpetX from Carpet. And of course, you also have GRMX, which is another GRMHD code, and you would hear more about that from Professor Philip Mosta tomorrow. So on CarpetX, we have our new GRMHD code called Astrex, and Astrex is heavily derived from the previous, its parent code Spritz, and you would hear more about Spritz from Professor Giacomatto on Tuesday. And like Spritz, Astrex also evolves the vector potential instead of magnetic fields, and then you have, so this ensures the divergence-free condition of the magnetic field. And for the different reconstruction schemes, we have this ReconX module, which provides these reconstruction schemes like MinMod, PPM, Vino-Z, as well as MP5. And for flux solvers, we have these two, Lax-Fredericks and HLOE. And we also have another module for Conteprim, which is called Conteprim Factory. And it currently provides this 2D noble Conteprim as well as 1D Palanzola one. And we also have implemented support for 1D reprimand scheme, but this is only for now only CPU compatible, so we can't run them on GPUs yet. And we are planning to implement other couple of Conteprims too. In terms of equation of state driver, we have another module called EOSX, and this currently provides just the simplest analytical equations of state, like idle gas and polytropic. And probably one of the goals of the workshop that's coming up next week would be to extend this to, say, a tabulated equation state as well. And lastly, we have the vector potential evolution, and for that you need to compute the electric field. And for that we have implemented the simplest flux CT approach as well as Upton CT as well. And AsterX is publicly available on GitHub in case you would like to check it out. And after all our implementations, we performed different kinds of tests to check the robustness as well as the accuracy. So starting with the simplest shock tube test. So here you see the results of the final time profiles of a Balsara shock tube test, which is magnetized. So on the left is you have the rest mass density. We can also have the exact solution that we compare our results with, and also the Spitz code. And on the right, we have the Y component of the magnetic field. So we find decent match between all of them. And this is similarly for Balsara 2, Balsara 3, Balsara 4, and Balsara 5. And then after doing these 1D tests, we performed some 2D tests. And some of this you probably would, there's a tutorial coming up on Thursday. Some of this you might be performing yourself with AsterX. So this is essentially a cylindrical blast test, and we find these final time profiles to be quite matching with what is considered in literature. Next is, this is again a 2D test where you have a rapidly rotating cylinder in a magnetized medium. And here too, we find profiles that are quite matching with what we have in the literature. And the next one is a loop advection. So you have this magnetic field loop moving across, and we have periodic boundary conditions here. So we see that with carpet X, we have such features, essentially periodic boundary conditions that we can impose. Finally, the last 2D test was this Kelvin-Helmholtz instability test, where we add a perturbation along for the Y component of the velocity. And we also try to play a little bit with the AMR policy or the criteria here. And we see that, I don't know if it's visible, but you have these dynamical AMR that it's gathering more towards these curls of here. So we still need to improvise on our AMR strategy for sure. I think this is very problem dependent. For now, this is what we have working. So the final test we did was a magnetized TO wave. And this is, for now, performed only in cowling. So we don't evolve the space-time. And we impose an initial dipolar magnetic field confined inside the TOV star with a maximum field of about 5 times 10 to the power 15 Gauss. And yeah, the evolution is basically using idle gas. And on the right, you see, for instance, for one of the cases where you have the evolution of the rest mass density, maximum of the rest mass density. And here you also see the 2D movies of rest mass density of the left and of the magnetic field component BX on the right. And up to now, the evolution seemed kind of fine. So we are very hopeful that this works without problems. But what happens when you switch on space-time evolution? So you see that there is a lot of, so on the right, you have the evolution of the excess component of the 3 metric, and you see there's a lot of reflections coming, and that essentially screws up your whole evolution. So we currently want to, another main goal of the workshop coming next week would be to implement radiated boundary conditions, so that we that can allow better evolution for such system. We did some scalings as well for carpet versus carpet X. This is again not 100% apples to apples because of course the infrastructure is different, but we tried to evolve as similar as possible a system which is essentially in this case a binary black hole. And we saw that when evolving with subcycling time with carpet, I mean in carpet X we don't have subcycling yet. So without subcycling, with subcycling in carpet, we saw that for the initial number of nodes we have carpet doing a better job, but later on carpet X takes over. And certainly when we switch off subcycling in time for carpet, we see that carpet X certainly does a much better job. In terms of GPU scaling, so recently we had a workshop organized by this Frontier on the Frontier cluster, OLCF. So we did some scaling tests there as well. And we found that we were able to improve the performance, but we still need to do a better job. So here you have scaling tests for a TOV star again, and evolving also the Z4C, but in case we evolve for just a couple of iterations. So it doesn't affect evolution much, but we can get some insights on the performance. And we do see, for the strong scaling test, we do see a fall off for about 50% or more. So this needs to be better, but weak scaling tests also the efficiency goes down for about 50%. So this is something we're still looking at. And the way to do that is to do using profiling. So what we essentially do is we want to profile the code. So we evolve our system, and this was done using NVIDIA Insight system, and it tells us which part of the code is taking, what are the bottlenecks, which is taking the most computation time. And for instance, you might see here, so this was a CPU workload, and then in black, and then you have the in bluish color, you have the GPU workload. Oh, sorry. And then you have the memory transfer, which is denoted in red. So you want to make sure that there is not more when you're running inside the GPU kernels, when you're running the for loops, you want to make sure that there is not. You want to minimize as much as possible this memory transference. So this is a good sign that things are working fine when you're actually doing these iterations, evolving your time steps. But still, this profiling helped us understand that. And recently, we also profiled our code using HPC Toolkit, and this also helped us identify these bottlenecks. For instance, probably not so clear, but here you see that for when you're computing the fluxes, this is essentially taking most of your computation time. So 7.8% out of the 10% is fluxes. So we need to try to understand how to optimize this as well. And Asterix is certainly a work in progress. We want to extend again the OS X and Quantum Factory modules and extend our scaling tests too. And we also want to explore these error estimator criteria for AMRs. How you want to dynamically adjust your grids and eventually perform BNS and supermassive binary black hole mergers. And just a reminder, we have an Asterix tutorial on Thursday, so stay tuned for that. And with that, I'll stop here. Thank you very much.
Questions? Yes.
I know that Spritz has also high order methods implemented. Will that do this too?
Right, so we already have implemented, so Spritz has Vino Z implemented. So we already have Vino Z here too. It's almost ready. We are testing it. So it works perfectly fine with 1D and 2D tests. With 3D tests, we're currently seeing some minor problems, but that's probably a bug in the code somewhere else. So we're still trying to find that. And Amplify works fine too. So these are all the methods, if that's what we're referring to.
Not exactly. It's a finite difference code.
Right.
Yeah. So then do you hope? Okay. Okay, so you do a component-wise reconstruction on the classes, or do you do a characteristic reconstruction?
I think we do it component-wise, if I'm not wrong.
Okay. Yeah, maybe that's okay.
Sure.
Here's a comment in the chat.
Oh.
Who wants it?
So the question is, can you comment on whether the GRMHD evolution for the E&M field outflow far away from sources could potentially be computationally heavy or unstable or not at all?
Oh, that's a good question. So this probably is referring to the AMR that we might adopt. So this is an unexplored territory. So I'm assuming the question relates to if you have some AMR strategy when you have the outflows going away from the source, but do you have any criteria on how to compute or follow that outflow? But so we haven't reached that point yet, if I understood your the question correctly. So
Yeah.
so we haven't reached the point yet.
We have another question.
Thank you.
I have a quick question for the TOV tests. How far was the outer boundary compared to the radius of the star?
Right. So for the cowling, it didn't make much of a difference. So for simplicity, we just put the outer boundary to like 20 m or 20 practice units, if you want to call it that way. Also for so when I showed this for also when evolving the metric, this is where you see the reflections. The outer boundary is still around 20 m, and the radius is about, if I remember correctly, 8 m or 8 captors units. So certainly this this is very close. You might, of course, if you extend the boundaries to about say 100 or 1,000 m, you certainly the reflections might take some time to the effects to come affect the star evolution. But I mean, this problem certainly still needs to be addressed quickly.
Anything else in the chat? Any other questions?
Yeah.
Yes.
Do you have data movements to the GPU calculate explicitly, or is that something that is handled by MRX automatically?
Oh, sorry, could you repeat the first part?
Do you have any explicit data movements in AsterX, or is anything related to data movement from host to device and back handled by MRX?
I think data movement. So I think it's typically handled by MRX and basically CarpetX.
Yeah, it's unified shared memory.
Yeah.
It's not just unified shared memory. There is no data movement. The data lives on the GPU all the time. And ideally, you also have an GPU-aware MPI implementation that copies the data directly from the GPU to another GPU. And then you only have data movement if you want to write them to disk, for example, or set up initial conditions.
Anyone else?
I would like to say it's very nice talk. Thank you for your presentation. And I may have a question regarding moving to AsterX is a question mostly of performance, or the fact that this splits base is also an improvement on treating whatever neutron star, station, jets, shocks, all of them, none of them.
Yeah.
What do you expect to gain?
Right. So main selling points, one of them is moving to running your simulation of GPUs, and that can be maybe you can reach excess scalable limits. And the second point is you also have some features that are provided by CarpetX, for example, refluxing, for instance, that might not be, we don't have such capabilities, at least implemented in sprids or related. So refluxing could be one good facility that we get. And third is the AMR itself. So when sprids or carpet-based codes, you have these box-in-box AMR, while here you can have these block structured. So this might, so of course, at least for us, we haven't explored that yet, but if you want to follow, some part of an outflow that is coming out or a jet, you can refine in that region and things like that. Or even if you want to resolve Kelvin-Helmholtz instability, where you are limited by certain, you might have to, what we do essentially, you can have just refining at the shear layer where it develops, you can just refine there. So this could have very good potential applications that way. But of course, we haven't got there yet.
We have one more question.